Hi, my name is Dylan and today's video is on searching. A lot of computer science problems require the use of searching to find a piece of information in a large data set. The way we find that information is called the search algorithm, and today we'll be covering binary and linear searching. So now we're going to look at the pseudocode for a linear search. You can see in the top row I have the numbers I'm going to search through. There are 8 numbers in total, which means because we start at 0, I'm going to have the maximum of 7 as my index. So I have 8 numbers here and they go from 0 to 7 as their index in the array. Now what I'm going to look for is the key 36. It's easy for us to see that 36 is obviously in the array, but this is a trivial example and we can expand this to 1 million numbers or 2 million numbers where you wouldn't be able to quickly look that up. However, this search algorithm will work for any size array. Now the linear search starts at a number and just slowly checks every other number. Because we're working in an array, it would make sense to start at the beginning, which is index 0, and go till we reach size minus 1, which in this case is index 7. So that's what I'm going to put as my current index. I'm going to start at 0. Now once we've started, the very next thing we do is we go over to this array here. I'm going to say check what's in index 0. So that will be a 1. Now we're looking for 36, which is clearly not 1. So we go through again and we say increment our index. So we go 1. We go back to here. And we see that 4, which is still not 36, which means we need to go again. And in fact, we're going to do this another 3 times. So we'll go 9. This will be the 16, the 25. Now, we find that our key wasn't 25, so we increment once more. And now we're looking at index number 5. In this index, we have the number 36, which is our key. So what we're going to do is we're going to stop there and report that we found it. Now, if we're looking for the number, say 100 in this example, we would keep going at this point. We'd say index 6, which would be 49, and we'd say index 7, which is 64. Now, as you can see, when we go to increment the index again, we end up with an index 8. However, 8 is greater than our size minus 1, which means our condition is false, and we can say that we didn't find the number in the previous array. So now we're going to code our solution in VLab. So the first thing to do is open up a terminal. I'm on the desktop now, so I'm going to go into my home directory, and then I'm going to change into a folder called search where I'm going to work. If I ls in this directory, you'll see I already have 2 files made, binary search and linear search. These are just subcodes that we're going to fill in. So the first thing I'm going to do is open up linear search by typing gedit space, the name, linearsearch.c, and then an ampersand, which will allow me to continue to use this terminal while gedit is open. So as you'll see, there is some code. We import the standard libraries. We're defining a few constants. And I have this function printArray, which we don't need to worry about, but will help us debug the program. I've declared an array that has 20 numbers in it, and they're all sorted. And I have a key which I'll be looking for, which is the number 87. So the first thing we need to do when we have a linear search is we'll need to keep a count of where we're up to. So I'm going to need another variable called I. Now, because we're working with arrays, it would be smart to start at the beginning of the array. And since array is a 0 index, we're going to set I equal to 0, and then a semicolon. Now, we'll be continuing to increment this through the array, so we're going to need a loop. So I'll write while I. Now we want to stop when we go off the end of the array, and the size of the array is declared as max size in the hash define. So I'm going to say while I is less than max size. We don't want it to be less than or equal to max size. Since the array is a 0 index, the max size is actually not in the array, like we saw in the pseudocode demonstration. The very next thing I do is update the condition, which is to go I equals I plus 1. So this means we'll start at 0, go 1, 2, 3, all the way through to 19, which is exactly what we want. Now we need to include our check. So we're looking for the key. So the first thing we should do is say if. We'll say if key is equal to, and what we want it to be equal to is the index of our nums array. So we'll say our array nums at index I. And we'll close off that if and open up some brackets. Now, if we do find the key in nums, let's print a message called success. And we'll say where we found the number. So we'll say %d, the number we found, was found at index %d. And then what we're going to be passing in is our key, and we'll be passing in the index I. Now, if we find the number, this will still keep looking through the rest of the numbers until the end of the array, until I equals max size. But we don't need to go all the way once we found the number. So we're going to have another condition in our loop, which says to stop the program when we found it. To do this, I'm going to have another variable called int found, and I'm going to set it to false. Now, I could set this to true and false is ones and zeros. However, ones and zeros tend to be quite ambiguous, and they're magic numbers. It's much nicer if we hash define true as 1 and false as 0, and then throughout our code we can simply write false and true where we would need it. So in this if condition, I'm going to change the next line to found equals true. This still won't break our while loop, as there's no condition here on found. So we'll add it by adding ampersand ampersand, which stands for and. We'll say found equals false. So while I is less than max size and found is equal to false, do our searching. When this is done, we can check that found is still false, which means that we didn't find the number. So at the bottom I'm going to have an if condition, and I'm going to say if found equals to false. Then what I'm going to do is print out we did not find the number. So I'm going to say printf could not find %d in nums, and a new line. The value we're passing into %d is going to be our key. So now what our code reads as is we're going to start at I, and we're going to have found as false. While I is less than the max size and found is false, we're going to check that key is equal to the nums at I, and printf if it is. Otherwise, we're just going to keep incrementing I. If we don't find it and found was never set to true, then we can print out an error message and we're done. Now, I'm going to use that print function from before so we can see these steps as they come through. So I'm going to say print array, pass in the size of the array, nums, and for this function to work, I also need to pass in I. Awesome. So I'll save that and push it to the side. Now if I go back into the terminal, I can use the compile command dcc to turn this into an executable. So I'm going to go dcc linearsearch.c. I'm going to output -o to a file called linearsearch and click enter. Now if I ls again, you'll see we have an executable called linearsearch. I'm going to go /linearsearch. And you can see here a representation of the steps that we went through. So initially, when we started, we only checked the first value and it turned out to be 4. The asterisks here represent numbers that we don't know the value of yet, and the dashes represent numbers that we can discard. So it wasn't 4, and we kept going 9, 14. We had to go all the way to the 4th last element to find our number. And in total, you can see that it took 12 steps to find that number. So we're going to implement the same thing with a binary search now and compare the two results. So here I have a phone book. Now if I wanted to find someone's phone number, I'd have to look them up by their names. Let's use Taylor as an example. Now one way would be for me to go through every single page in the book until I found what I was looking for. However, that would be incredibly slow, and it means every time I turned the page, I still had to check the rest. I'm only decreasing the search space by 1 every time. There is a fast way though. We know that the book is sorted by name. So what we're going to do is we're going to open up to the middle, and we're going to check that the current value, if it's less than or greater than what we're looking for. So I know that Mahoney comes before Taylor in the alphabet. So I'm going to discard the first half and grab this second half here. Now if I do the same thing again by splitting it in half, I now have Rushby, which is again before Taylor. So what I'm going to do is discard the half I just picked up and go again. And now we're getting a lot closer. Now I'm at Donette, which is after Taylor. So I'm going to grab this final half, open it up, and you'll see I hit Taylor. So I hit Taylor in 5 steps, which is a lot quicker than the 1,000 it took to do a linear search. So what we just did was the binary search, and it's just as simple as that. We just open up to halfway, and we check for higher or lower. Okay, so now we're going to look at the implementation of a binary search. So to start with, I again have the same array of numbers, 1 through to 64, and there are 8 of them, which means that I have indexes 0 through to 7, which is the array length minus 1, as we saw before, and now I'm going to look for the key of 9. So to start off with my binary search, I'm going to need to find the mid. And to find the mid, we're going to take the average of the first and last. Just like in a linear search, the first will start off as 0, as that's the first element in the array. The last will be the length of the array minus 1, which in this case is 7, which means that the mid becomes the average of these two, which is 3.5. Now, luckily C division chops off the 0.5, and we leave our mid as 3, which is awesome. So we'll go over to 3, and in 3, we have the number 16. Now we're looking for 9, and 9 is less than 16. So now what we're going to do is we're going to move our last number. We're going to discard this, and we're going to just look in those last 3 boxes there. So we're going to say our last becomes the mid minus 1. So our previous mid was 3, which makes our new mid 2, and the first doesn't change. So in this, we have first here and last here. Now what we're going to do is we're going to find the mid, which is the average of the 2, which will be 1. And now we're going to look at index 1. So index 1 contains 4. We compare 4 to our key of 9. 9 is greater than 4. Therefore, the last will stay the same. Our first now gets changed to the previous mid plus 1. So our first becomes 2, and that means our mid, which is the average of 2 and 2, is also 2. So we're going to be checking this box here, and we find at index 2 we have 9, which is our key. So we could stop here and print out a error, like a success message. What I want to try though is say, what happens if our key was 10? So we would have gone through the same steps. We would have started off in box 3, we would have said that 10 is less than 16. We would have found 4, said that 10 was greater than 4, and we would arrive at the same place of 9. Now 10 is greater than 9. I don't have anywhere in this array that 10 could sit, which we know means that it's not in the array, but this will be how our loop terminates if the value is not found. We increment as normal, so 10 is greater than 9, which means we move first to the previous mid plus 1. So first becomes 3, last doesn't change. And now what we see is that first is greater than last. And this is when we'll stop and we'll say that the number is not in our array. So I'm going to open up Get It by typing Get It, the name of the file, binarysearch.c, and then an ampersand so I can continue to use the terminal. You'll see the stub code we had before with our includes, our defines, and this print array which we don't really need to worry about. I've also got the exact same array declared of numbers, and I have a key which I'll look for, which I'm going to look for 87. Now, the very first thing we need when we're doing a binary search is the middle. And to find it, we're going to need to know the first and the last index that we're currently looking at. So I'm going to create an integer variable. I'm going to call it first. I'm going to create another one called last. I'm also going to need the middle, so I'm going to put that in a variable as well, and for convenience I'm going to do this all in one line, and I'm going to initialize each of them. So we know that first will be 0, as that's the first index of an array. Last will be the size of the array, subtracting 1, because it is 0 indexed, max size actually goes off the end of the array, and the middle is the average of first and last. So we're going to say first plus last over 2. Now we need to make our loop. So we're going to need a while loop, and the condition for a binary search is that first is less than or equal to last. So we're going to write exactly that. First is less than or equal to last. I'm going to open up some braces. Now I have initialized middle up here, but every time this loop iterates, I'm going to want the middle to be the new average of the first and last. So I'm actually going to move that into the loop by just cutting and pasting. Now, we need to update our condition, so either first or last will need to change. So, if our key is less than the nums at the current mid, which means that what we're looking for is in that first half. We need to adjust our last index. So how we do that is we say that last is equal to the previous mid minus 1. Now, if the key was not less than nums, we're also going to check else if the key was greater than nums mid. Closing that off, opening up braces. Now we're going to do the exact same thing, except this time first will get updated if it's in that second half. So I'm going to type first equals the mid plus 1. There's no point making first equal to the mid because we've already checked that that's not our value. If it's not less than and it's not greater than, then it must be equal to. So we're going to write else. We could just leave it as an else, but I'm going to also put it in an if just for a little bit of clarity. Key is equal to the mid. Sorry, is equal to the nums mid. Then we have found our number. So just like before we did in the linear search, we're going to print out a success message. So we're going to say printf. We're going to go %d was found at index %d, and I put a new line. Now we need to put in these variables, so I'm going to put in the key, and I'm also going to put in mid, which is the index we're currently looking at. Semicolon. Now, like we saw in the linear searching, this will just keep going even after it's found the number. So I'm going to add the same condition we added before, which was to have another variable called found. And found will start off as false. Now, remember, I've defined false up above because it's a lot simpler to read than having zeros and ones throughout your code. So we know that found starts off at false, and while it's false, we're going to keep looping. And then once we found it, we're going to set found to true, which will break our loop. What this means is we'll be able to check if we found our number or not by checking found after the loop is done. So we're going to go if found is still false, then what we're going to do is print out we didn't find the number. So we're going to go printf could not find %d in array, print out a new line, close it off, and we're going to pass in the key and put a semicolon. So that's it. That's how we do the binary search. We're going to save that. We'll go back into our terminal and we're going to type dcc binary search.c, and then we're going to output with the -o flag to an executable called binary search and hit enter. Now you'll see we forgot a bracket here, so we're just going to quickly add that in, which is why it helps to use DCC. And we'll run that again. Now when I run my file, binary search, you'll see that 87 was found at index 16. Now it would be nice if we got the printed output up before, so luckily I have a print array function, print array, which will do that for us. Again, you don't need to worry about the implementation too much. Just know that it will add a nice printing on every step. So we're going to go print array, pass in the size, the array, first and last. Close that off. Now we've made a change, so we're going to have to recompile our program. And we can run it again. And now you can see the steps that happened during the binary search. So we started off at our middle with the value 51. We know that 87 is greater than 51, so we can discard everything to the left of 51 inclusive. We calculate the new mid, and whose value is 81, which means that we can now discard the left bit as 87 is greater than 81, and we're left with these values here. Now the middle of that is 90. Since 87 is less than 90, we're going to discard the right hand side this time. I'm going to be left with these two values. Now we take the middle of that, which is 86. We know that 87 is greater than 86, so it leaves us one value to check. And there we have found 87. Now you can see this only took 5 steps instead of the 16 it took before. So it is a lot quicker. It also will find numbers that aren't in the array. So we can check that our number wasn't in an array. So I'm going to put in a new key. And I know that 100 wasn't in the array, so I'm going to save it with 100. I'm going to recompile because I've changed the key. And I'm going to run that once more. And so you see what happens this time. The initial steps are the same. 100 is greater than 51, so we discard the left-hand side. The new mid, 81, is still less than 100. Discard the left-hand side. We calculate the new mid again, 90, and you see how we step down. We get to the end value here. There are no more values to check, and that last value isn't 100. So what happens on this step is that first actually exceeds last now, and our loop will stop and found never got set. So our condition where we couldn't find the number gets printed, and we see that 100 was not in the array. Thanks. So that's all there is to linear and binary searching. The two important takeaways from this is that binary searching only works on sorted data, and that, in general, the search algorithm we choose is related to the way that the data is stored.